These are BC Calculus Notes 6-4. Let's go ahead and do some quick reviewing. First of all, let's start off with a limit. If we have a limit as x goes to 2, one way of solving that is by just plain old direct substitution. In this particular case, I'm just going to take the x and evaluate that. As x gets closer and closer to 2, it's going to act like 2. And of course, that would give us 2 squared, which is 4, minus 3, and our value would be 1. Okay. Next, we may have to, when we're evaluating a limit, we may have to do a little bit of algebra. You can see in this first one, if we were to do this by direct substitution, the result would be a 0 divided by 0, which means this is going to be undefined and what we'll call an indeterminate form. But with a little bit of algebra, we recognize that our numerator would actually, so we go the limit as x goes to 3, it would factor to x minus 3 times the quantity of x plus 3, all divided by x minus 3. These two, of course, would factor out, and the result would be the limit as x approaches 3 of x plus 3, which of course would be 3 plus 3, and we could do just like we did up above and just finish with some direct substitution. Similarly, in the next one, you can see that if we were to evaluate this, the limit as x goes to 2 of x minus 2 would give us 0. And in our denominator, the limit as x goes to 2 of x squared minus 3x plus 2, that would be 4 minus 6 plus 2, which is also going to give us 0. And we have the same thing that we described over here, that case where we've got a 0 divided by 0, which is an indeterminate form. But a little bit of factoring goes a long way. In this particular case, if we factor the denominator, that denominator would factor to x minus 2 times the quantity of x plus 1, which is simplified to the limit as x goes to 2 of 1 over x plus 1, which would be, I think that's should be a minus 1 there, looking a little bit closer. That would give us the positive 2 and a negative 3 in there. That correction would give us a 1 over 2 minus 1, or 1 divided by 1, or 1 on this one. Okay. Next, when we evaluate our limits, we also want to consider what we refer to as our infinity rules. Okay? As we look at these rational functions in each one of these examples here, A, B, C, and D, in these rational functions, we know there's a relationship between the numerator and the denominator that will give us a specific amount anytime we evaluate these. So first of all, let's look at the first one here. As x goes to infinity, x is going to get really, really big. It doesn't matter how big the numerator is. The denominator here is going to get huge, and eventually it's going to approach and go to 0 here. Okay? But if we flip this around, the numerator, no matter what you're going to divide it by, if the numerator goes to infinity, it's going to get so big that we're actually not going to be able to go to a specific value, and this is going to end up going to infinity. Or what we would say on this limit, it does not exist because infinity is not a number. When we're looking for a limit, we're looking for some number that we get that then we would stop at. Let's consider the case when x is going to 0 in a set of rational functions. As x, the denominator, goes to 0, it's getting smaller and smaller and smaller. If we take any number and divide it by any number besides 0 and divide it by a number that's approaching 0, this is going to be acting almost like the last one. We're going to get a value that goes to infinity, which again is not a number, so this one does not exist. Let's consider this case. As x gets smaller, or excuse me, as x gets smaller and smaller here, it's going to get closer and closer to 0. This number down here, again, as long as that's not 0, this is going to approach 0. Okay? So these two cases, we have a definite value that we're going to get. These two cases will be an undefined because our limit is going to infinity. Okay? Let's also take a look at a couple rules concerning how we evaluate limits. First one is, what happens when we have two functions added together and we're evaluating them as x goes to infinity? Well, if it's easier for us, we can take the limit as x goes to a of f of x and then add or subtract the limit as x goes to a of g of x. Okay? We can evaluate those separately. With multiplication, same thing. We can evaluate the limit as x goes to a of f of x and then multiply that by the limit as x goes to a of g of x. And the same thing can happen with our division. In our division problem, if we want to, if it works out better for us, to evaluate the limit as x goes to a of f of x first, and then divide that by the limit as x goes to a of g of x second, that's a rule that we can apply at any time. Okay? Let's take a look at these scenarios and each one of these cases in our examples here. Okay? So first of all, notice in this one, as x limit as x goes to 5 of x minus 5, that's going to give us 0. So this is similar to the one that we just had up above here in C. If our denominator is going to 0, the result will be some number, 2, divided by some number that's getting really, really small, going to 0. So this will be an infinity or a does not exist if we were to answer that specifically. Let's take a look at the next one. In this case, the limit as x goes to 5, x minus 5 is just going to give us 0. This is going to be 0 divided by 2, or 0. We can just substitute in on this one. Okay. Next, we have a case where x is not going to a real number. It's just getting bigger and bigger. It's going to infinity. And that's going to be the case that's similar to b up above. We're going to get infinity divided by 2, which of course would be infinity, or a does not exist. Let's take a look at our next one. In this one, it's our denominator now that's going to infinity. Okay? As that denominator goes to infinity, and we have this limit as x goes to infinity of x minus 5 being infinity, we'll have the case where we have a number 2 divided by infinity, which of course is going to be 0. Okay. Next, we have two limits here. In the first one, this is similar to case C up above, where we're going to get a denominator that's going to be so huge compared to the numerator, this is going to go to 0. And then, of course, infinity cubed is still going to be infinity. And this gives us a case where this is what would be called an indeterminate form. 0 times infinity may not necessarily be infinity. What we can do is apply this rule up here, which says we can split them up and evaluate them individually, or we can rewrite it as a rational function and then solve it. We could write this as x goes to infinity of x cubed divided by x squared, which simply would simplify to the limit as x goes to infinity of x, which of course is infinity. In this case, 0 times infinity is going to give us an infinity, or does not exist. Let's take a look at our next example. Same pattern we saw on this one. Okay, first one is going to be a 0. Second one's going to be infinity. So I do apologize there. Didn't realize that was off the screen. So real quickly repeating, we get 0 here. We get infinity here. Rewrite it as a rational function, simplifies to x, and then we go to infinity. This time, we're going to do the same thing, apply this rule, and rewrite this algebraically as the limit as x goes to infinity of x squared over x to the 5th. The result will be, evaluating as x goes to infinity, of 1 over x cubed, which means our denominator is the one that's going to infinity, similar to a up above, and this is going to result in us getting 0 here. 0 times infinity doesn't exist, or 0 times infinity, in this case, equals 0. Let's check the next one. In this case, we get another example of a huge number in the denominator that keeps getting bigger and bigger, so this is going to go to 0 times infinity squared, which of course will be infinity. Apply our algebra, the limit as x goes to infinity. This would be x squared in the numerator and 2 to the x in our denominator. But this does kind of leave us in a dilemma here, because this one does not simplify. Okay. If this can't simplify, we might need to use something else, and that's what we're going to cover next, a way to evaluate these when they are in a form that's indeterminate. As you can see here, of 8, 9, and actually 10, we were able to evaluate 8 and 9 by using our limit laws and algebra. Unfortunately, with example number 10, we ended up with something that would be considered an infinity divided by infinity. Will this equal 1? Will this equal 0? Will it be infinity or some other number? Okay. You may have an opinion on that, but I'm here to tell you that sometimes when we have infinity divided by infinity, it's going to do what we call converge. It's going to go to some number, and we can say exactly what that number is. Your gut may be, hey, it might be 1. Or your gut may be, it might be 0. Well, you're correct. It might be, but it may not always be. Because sometimes they will not converge. Okay? Anytime we have a case like this, we have to do some more work. Okay? This infinity divided by infinity is called an indeterminate form. There are other examples. We could have 0 divided by 0. We could have 0 times infinity. Obviously, you kind of see from these examples up here, 0 times infinity sometimes gives us a number, in this case 0. Sometimes it doesn't give us a number. We go to infinity. Okay? And then some other ones that we will run across is we might get infinity minus infinity. We might get 1 to the infinity, or infinity to the 0 power. Think about that one. Okay, is that 1? Don't know. It's indeterminate. And this one, a 0 to 0 power. Is that 1? Since we said anything to the 0 power. So when we run into indeterminate forms, there is one rule that we can apply if they are of these forms. It's called the L'Hopital rule. Using L'Hopital, what we can do is, if our numerator is going to infinity and at the same time our denominator is going to infinity, and we could care less about the signs, whether they're positive or negative, we will apply this rule. Or, that's the important thing, or if it's a 0 divided by 0. If we evaluate the numerator function, and it's going to 0 as x goes to whatever value we're looking for. And the same thing happens in our denominator. We will apply the L'Hopital. It is only these two forms that we're allowed to. Any of these indeterminate forms will not use L'Hopital. We're going to learn maybe a couple ways that we can manipulate these to apply it, but in this case, no, it doesn't. And again, here's what it says. If we get it like this, what we can do is take the derivative of the numerator and then take the derivative of the denominator and reevaluate our limit. This is not the quotient rule. I want to repeat, this is not the quotient rule. Okay? So here are the procedures that we'll use when we're evaluating this. Okay? So first of all, we must first explicitly show that our numerator is 0 or that it is plus or minus infinity. Then we'll also show that the denominator is, this should say, denominator. The denominator is 0 or goes to plus or minus infinity. Okay? You'll see online, you'll see a lot of people write this as, hey, we get 0 divided by 0 or infinity divided by infinity, which is okay to note, but I'm bringing this up to you because AP rules say don't write it like this. Evaluate the numerator, evaluate the denominator, and then state that we have an indeterminate form. Because the numerator and again, I'm not sure why this says numerator twice, but this should be denominator, are both 0 or they are both infinity. And again, it doesn't matter whether it's a plus or minus on the infinity. Okay? So then what we would do is we would rewrite our limit. We started off with something that could have been as x goes to a of f of x over g of x, and we had the indeterminate forms. We would rewrite this by taking the derivative of the numerator, f prime of x, and separately the derivative of the denominator. Okay? Then we would simplify this. Okay? It might be necessary to repeat the steps over and over again. Similar like we did with our tic-tac-toe, similar when we have our chain rule. Okay? Where it didn't work one time, let's do it again. Okay? And then I'll try and note here as we go through, make sure as you're doing these that you are following proper limit notation throughout the solution. That's something that will give lose easy points on your AP exam, or of course on our tests or quizzes. Okay? Some helpful hints. In order for the L'Hopital rule to apply, you must have indeterminate forms of that 0 divided by 0 or an infinity divided by infinity. Only that. Okay? If it's not of that form, then we're going to change that to a division limit. Okay? Apply a little bit of algebra to make sure it looks like a rational function and we can have a division. Okay? So, like I said and mentioned on the previous page, if we end up with something like an infinity minus infinity, or a 0 times infinity, or a 0 to the 0 power, a 1 to infinity, or an infinity to the 0 power, we might want to apply some algebra skills to try and get it to look like this. Okay? Next, the limiting value of a can be any number. Okay? Or it could also be positive or negative infinity. And L'Hopital's rule will still apply with our one-sided limits. If you remember all the way back to something like the limit as x goes to 5 from the left, something like that, that would apply. Okay? L'Hopital's rule as I've stated, or it was stated up in the procedure up above, it could be repeated. And what we're going to do is use it as many times as possible. Okay. And please, not the quotient rule. You don't have to do any high deload, low d high, all over low squared. None of that. Okay. It's just derivative numerator, derivative denominator. Okay. These do not require L'Hopital or anything else. If you have infinity and you add infinity, it's definitely going to be infinity. Or if you're going to negative infinity and you subtract infinity, you're still going to go to negative infinity. All right, so our first one. In this case, if we evaluate the limit as x goes to 0 of the sine of x, we're going to go to 0. If we also evaluate the limit as x goes to 0 of x, that will also be 0. Okay? Which now we can say this is an indeterminate form. Okay? And we can go ahead and apply L'Hopital. And I know it looks like La Hospital, but there is no S in L'Hopital. So this would give us the derivative of sine. Sorry, let me put my limits in here because we are going to show proper notation throughout. The limit as x goes to 0. The derivative of sine is cosine of x. The derivative of x is 1. When we evaluate this, it's simple algebra. Cosine of 0 is 1. 1 divided by 1 is 1. And just a quick note for you, if you remember and have this graph hopefully memorized, remember our sine of x, if we've got f of x equals the sine of x divided by x, that was our ripple. Our ripple graph went like this, kind of down to 0 this direction, and then also to infinity in this direction. But obviously, it was undefined at x equals 0. X could not equal 0. And look at this. From the left and the right, this is going to 1. So the limit of, as x goes to 0, of sine of x divided by sine of x is indeed going to be 1. Now, let's take a look at our next one. In this case, if we evaluate the limit as x goes to 1 of the natural log of x, that will be the natural log of 1, which is 0. If we evaluate the limit as x goes to 1 of x minus 1, we'll get 1 minus 1, which is 0. So we'll make this case that this is an indeterminate form. So our L'Hopital applies. With L'Hopital, we take the derivative of the numerator. We're still taking the limit as x goes to 1. The derivative of the numerator is 1 over x. The derivative of the denominator is 1. We can evaluate this algebraically by just substituting in 1. 1 divided by 1 divided by 1 is 1. And we're done. We have a couple more examples to work through. Let's see what we got on these. So, first one. Again, we're going to evaluate this as the limit as x goes to infinity of e to the x. That's going to be e to the infinity, or infinity. The limit as x goes to infinity of x squared. And that's also going to be infinity. And therefore, this is indeterminate. L'Hopital does apply. So, derivative of the numerator is e to the x. Derivative of the denominator is 2x. Notice this time we still have an infinity divided by infinity. In other words, as we are going to note here, the limit as x goes to infinity of e to the x is infinity. The limit as x goes to infinity of 2 to the x is also infinity. So let's take the derivative again of this. Limit as x goes to infinity. Please show proper form. Do not drop the limits until the x's are gone. This is going to give us e to the x. Derivative of 2x is just 2. This time we'll have e to the infinity divided by 2. Half of infinity is still infinity, so this limit actually does not exist. Let's take a look at our next one. When we evaluate the limit as x goes to infinity of the natural log of x, that will be infinity. The limit as x goes to infinity of the cube root of x is also infinity. This is an indeterminate form. Therefore, our L'Hopital will apply. Okay. So, derivative of the numerator is simply 1 over x. And then think about this. This is x to the 1/3. So subtract 1, x to the negative 2/3, multiplied by, I forgot to bring the exponent down first. So bring down the exponent, 1/3, subtract by 1, and we have this. Okay. A little bit of algebra can be used here. This is x to the negative first power divided by 1/3 times x to the negative 2/3 power. Okay. So when we evaluate this algebraically, this will be the limit as x goes to infinity. The 1/3 gets a reciprocal, or turns into a reciprocal since it's in the denominator, so that's going to be 3. And then think about this as a negative 1, subtract a negative 2/3, which is going to give us x to the negative 1/3 power. Okay. And as x goes to infinity here, remember that negative exponent is going to put this in the denominator. We're going to have that 0, or in this case, 3 divided by infinity, which is going to go to 0. Next, we've got a case where the limit as x goes to 0 from the right of sine of x would be 0. Sine of 0 is 0. And the limit as x goes to 0 from the right of x squared is also going to be 0. We have an indeterminate form. Therefore, L'Hopital will apply. So, let's take our derivatives here. Limit as x goes to 0 from the right. Derivative of sine of x is cosine of x. Derivative of our denominator is going to be 2x. As x goes to 0, this is going to end up being 1 divided by 0, okay, which we know can't exist Therefore, this is an infinity, or a does not exist. Okay. What if we try this from the other side? Well, the limit as x goes to 0 from the left of sine of x is still going to be 0. The limit as x goes to 0 from the left of x squared is still going to be 0. We have this indeterminate form, and when we evaluate this, the limit as x goes to 0 from the left, we'll have the derivative of sine, cosine of x, derivative of x squared, 2x. And this one, be careful here, just because of the notation, we know that this is going to be a 1 divided by 0, and it's going to be a does not exist, but this one actually is not going to infinity. This one's actually going to negative infinity, because think about this, the 2x, as x goes to 0 from the left, this is going to be smaller and smaller negative numbers. Okay, so this is going to be actually 0 from the left that we're getting to. So just to be careful, sometimes there might be a need to evaluate this and be specific about whether we're going to infinity or negative infinity, and this is one of those cases. Let's take a look at our next one. Okay. In this one, as x goes to infinity, you can see here with this one, we'll have the limit as x goes to infinity here of x. That's going to be infinity, but wait a second, e to the negative x, as that goes to infinity, this is actually going to be infinity times 0. This is not a L'Hopital problem. Okay? It's not of that form. We need to apply a little bit of algebra to this to get it to a L'Hopital form, and that's by rewriting it. We haven't taken any derivatives, we haven't evaluated any limits, but rewrite this as x over e to the x. This e to the negative x drops down there, and now you can see that we can evaluate the limit as x goes to e to the x. That's going to be infinity, so we have that case by rewriting it to this. Just by algebra, we'll have the infinity divided by infinity, which tells us that we are in indeterminate form, and L'Hopital applies. So we can take the derivative of the numerator, and that's 1. Derivative of the denominator is e to the x. As x gets bigger and bigger and bigger, the denominator is going to get bigger and bigger and bigger, and this is going to approach 0. Let's take a look at our next one. As x goes to 0 from the right, this x is going to be 0, but remember how the natural log graph looks. Okay? Our natural log graph looks like this guy here. So as x goes to 0 from the right, this is going to be a negative infinity. Negative infinity times 0 is not a L'Hopital problem. So what we're going to need to do is go ahead and rewrite this as the limit as x goes to 0 from the right of the natural log of x divided by 1 over x. We're going to rewrite this as 1 over x. Each one of these evaluated individually, the limit as x goes to 0 from the right of the natural log of x goes to negative infinity. The limit as x goes to 0 from the right of 1 over x is, in this case, going to go to a positive infinity. We've got infinity divided by infinity, therefore this is indeterminate, and we're going to apply L'Hopital. The derivative of the numerator, we're still writing our oops, that should be a 0, not infinity. The derivative of the numerator is 1 over x. The derivative of the denominator, bring down the negative 1, subtract 1, will look like this. We've got a x to the negative 1 divided by x to the negative second, and this is also going to be negative. This, I'm going to rewrite down here. This will simply be the limit as x goes to 0 from the right of negative x. Negative 1 minus a negative 2 would be a positive first power, which tells us this is going to go to 0 as x goes to 0. Let's take a look at our next one. Okay. From this one, if you remember what your secant graphs and your tangent graphs look like, as we go to 1/2 pi from the left, this is end up going to go to infinity, and this one's also going to go to infinity. This is an infinity minus infinity, indeterminate form, and also not a L'Hopital form. So what are we going to need to do? Well, we can apply some of our trig laws to this, and we'll still need to take the limit as x goes to 1/2 of pi divided from the left-hand side. And let's rewrite this as secant is, we know, 1 over the cosine of x, and tangent is always sine over cosine. Now that's somewhat convenient because we do have common denominators here. So we can rewrite this as the limit as x goes to 1/2 pi from the left of 1 minus the sine of x divided by the cosine of x. And think about it. If we're evaluating the limit as x goes to 1/2 pi from the left of 1 minus the sine of x, this is going to be a 1 minus 1 and give us a 0 in the numerator. Our denominator would be the limit as x goes to 1/2 pi from the left of cosine of x, which of course is 0. We have a 0 divided by 0. Therefore, this is an indeterminate form, and we're going to use our L'Hopital. L'Hopital will make this the limit as x goes to 1/2 of pi from the left. Derivative of 1, of course, is 0. Derivative of sine is cosine. Since that was a negative sign, we'll have a negative here. The derivative of cosine, though, is negative sine. And then we can simply solve this by substitution. 1/2 of pi is at cosine. Cosine of 1/2 of pi is 0. The sine of 1/2 of pi is 1. 1 divided by 0, or negative 1. I guess I should write that as negative 1. This is going to give us 0. Let's take a look at our next one. In this one, as we go to infinity, as the denominator goes to infinity, this is, 0. This is going to give us infinity. And of course, the sine of 0 is infinity. This is an infinity minus infinity. Same thing we had over here. That's an indeterminate form. It could be 0, could be something else. We have to evaluate this. So a little bit of algebra first. If we get common denominators of, write the limit here, limit as x goes to 0. If we get the common denominator of x times the sine of x, we would have to multiply both numerator and denominator here by sine of x. Of course, that's just 1 times the sine of x in the numerator. And on this side, we'd multiply numerator denominator by x. This would be and x. Okay. Then let's look at these individually. The limit as x goes to 0 from the left of the sine of x minus x would be a 0 minus 0, or 0. the limit as x goes to 0 from the left of x times the sine of x is 0 times 0, which is 0. Therefore, we have an indeterminate form. And L'Hopital will apply. So let's go back up here to this thing and take the derivative. Limit as x goes to 0 from the left. The derivative of sine is cosine of x minus 1, derivative of x. And then we do have a product rule here. Derivative of the first, keep the second. 1 times the sine of x. And then plus, product rule, keep the first, x, times the derivative of the second, which is the cosine of x. Okay. Now, if we evaluate these, look what happens when we evaluate the numerator. The limit as x goes to 0 from the left of the cosine of x minus 1 would be 1 minus 1, which is 0. The limit as x goes to 0 from the left of our denominator, the sine of x plus x times the cosine of x, would be 1 plus 0, which is also 0. So we have to apply L'Hopital again by taking the derivative of the numerator. We still haven't taken our limit here. This is still the limit as x goes to 0 from the left. Derivative of the numerator would be negative sine of x minus 0. Derivative of sine is cosine. And then we're going to add product rule again. Derivative of the first, keep the second, will be cosine of x. And then keep the first, x, times the derivative of the second, which would be a negative sine of x. Now, let's evaluate this as x goes to 0 from the left. This is going to give us negative 0, or just plain old 0. The denominator will be cosine of 0, which is 1, plus the cosine of 0, which is 1, and then minus 0 times 0, or minus 0. So this is 0 divided by 2, or 0.